My name is Tim Pierre. I'm a scientist, a physicist. I work at the University of Western Australia in the School of Physics, and I spend most of my time carrying out scientific research and teaching undergraduate students. I also help postgraduate students with their own research projects. I started my scientific career at school in England, where I studied physics, chemistry and mathematics at year 11 and 12 level. I then went to the University of Liverpool to study a physics degree. After that, I studied more physics by carrying out research for a PhD in physics. And during that time, I met Australian scientists who had interesting projects going on here in Perth. So I decided to follow the nice weather and come here to Australia. I came to join a scientific team at Murdoch University, and I studied under a position called a postdoctoral fellowship for 8 years, and then obtained a job at the University of Western Australia in the School of Physics here. I think I became a scientist because my interest in science stems from my childhood as far back as I can remember. My grandfather helped me by putting together a chemistry set out of spare parts from old chemist shops. And with the chemicals we put together, I had great fun in going out into the back shed and doing all sorts of experiments. But then I also obtained at some point a set of magnets which intrigued me. The fact that these objects could repel or attract each other at some distance from each other was completely fascinating. And that, together with a book I had, which was from the How and Why series that was available in those days, which was all about how electricity is generated. And I was fascinated by the fact that you could generate electricity by turning a magnet inside a coil of wire. To me, this was almost like magic. And from that point onwards, I think I was hooked as being a physicist. During my time in the upper school, I had to decide what I was going to do when I left school. So I knew I wanted to go to university and study a degree in science, maybe chemistry or engineering, physics. I looked at all of them, but it seemed to me that physics was the science that underpinned everything else. So that is why I decided to do a physics degree. While I was at university, I had great fun learning more and more about physics. But of course, I also had to think about what am I going to do when I finish at university. And I considered all sorts of possible job options. One option was to work for the Weather Bureau, because they require physicists in weather forecasting. I also was interested in joining one of the big telescope facilities and becoming an astronomer. I also looked at the possibility of going into industry, for example, the electricity generation industry and so on. And in the end, I couldn't quite decide what I wanted to do, and I felt that I wanted to learn even more physics. So I ended up deciding to continue in research at the university. And to do that, that meant doing a PhD in physics. My research in physics has taken me into the field of magnetic materials. And you might have some ideas about what you think magnetic materials are. Most people think about fridge magnets, for example. Perhaps the most common example of a magnetic material that we think about. We know that metal objects are very often magnetic. But interestingly, my research led me into the area of biological magnetism. And we don't often think about biological things being magnetic. But in biology, iron is a very important element. And it turns out that by studying the very subtle magnetism of biological objects, you can learn things about what's happening to the iron in those biological systems. So that's what I started carrying out my research on, That research has taken me into all sorts of interesting fields. I've had to deal with medical doctors, even patients. I've also dealt with chemists, biologists, agricultural scientists, geologists. It really has expanded my scientific horizons. In fact, I remember when I started university, at the very first lecture I went to, the professor of physics said to me, "When you leave this place, you will have a piece of paper in your hand called a physics degree, which is a piece of paper that will give you permission to stick your nose into anybody else's business." And so far, I found that he's been right. Sometimes people ask me what I will be doing in 10 years' time. The honest answer to that is, I don't know, because the beauty of being in scientific research is that you don't quite know where it's going to lead you. In fact, even as a science graduate, when you are learning about science at university, especially a subject like physics, what we can say is you are being trained for jobs that do not yet exist. So as technology advances, we will always need people who have a fundamental understanding of scientific principles, and that's what a science degree gives you. The focus of my current research is trying to understand the magnetic and physical properties of rust particles inside human beings. Now that may seem like a strange thing to do, but there are many diseases where patients build up too much iron in their body and it deposits in tissues in the form of rust. The rust itself does have subtle magnetic properties that we can measure externally from the body, which is good because doctors currently measure the amount of iron in the body by making incisions to take samples of tissue, such as a small piece of the liver, which they can take away for chemical analysis. This is an invasive procedure that is unpleasant for the patients and does carry some risk with it. So by exploiting the magnetic properties of the iron, which because of the fact that magnetic objects can interact at a large distance, enables us to probe the amount of iron in the liver externally. This enables us to develop technologies that are non-invasive for measuring the amount of iron in the liver, for example. And not only are they non-invasive, but they are more accurate than the biopsy methods. And so through this, we have been able to develop new technologies for hospitals. One of the really fun things about working as a scientist is that it gives you the opportunity to use all sorts of very interesting instruments and tools. These pieces of equipment are used to measure and detect all sorts of things. And some of the instruments that I've had the opportunity to use are things like magnetic resonance imaging machines or MRI machines that are found in most major hospitals today. They are expensive, they cost about $2 million each, so not everyone gets a chance to play with them, but we are able to do this. We're able to test out new ideas with them. We also use other instruments called magnetometers. These are used to measure how magnetic something is. And we also have the chance to use extremely big and expensive machines, things like the synchrotrons. These are very large instruments that cost hundreds of millions of dollars and are typically only found in a few places around the world. We're very lucky that we are having one built here in Australia, in Victoria. We use synchrotrons in our research because they are machines that generate very intense beams of X-rays. And we can use X-rays to study the microscopic structure of materials. And in our case, we're interested in studying the structure of particles of rust in samples of tissue from the human body, for example. What's important to us is to know how big these particles are and also how far apart they are. For example, the size of the particle is important because the smaller the particle, the more toxic it becomes. And so by measuring these particles in tissue samples, we can get an idea of the toxicity of the iron in those tissues. X-ray machines come in all shapes and sizes, and in the early days scientists built machines that you could fit on a lab bench, and it's these small machines that taught us how to use X-rays to study materials. However, in many experiments you need more flexibility, you need more intense X-rays, and also you need to be able to look at a much smaller part of the X-ray spectrum. In other words, you need to be able to vary the wavelength of the X-rays. And this is something that these smaller machines cannot do. As such, we need to go to the synchrotron machines, which have the ability to provide us with very intense beams, and also, because they are so intense, we can filter out certain parts of the X-ray spectrum and deal with very narrow bands of wavelength. As a scientific researcher, I use mathematics a lot in my everyday work. And sometimes people ask me which is more important, maths or science. It turns out that as scientists, we use maths as a tool. It is a very important tool for us. All scientists need to have a good grasp of mathematics to be good scientists. So really, there isn't a good answer to whether maths is more important than science. Maths supports science. I'm now going to try to explain to you how we used mathematics in the experiment that we carried out at the synchrotron to measure the size of iron particles in liver tissue. If you can imagine that the synchrotron is over here somewhere, and we do our experiment at the end of something called a beam line. The beam line is a long tube that emanates from the synchrotron, and out from which comes an X-ray beam. We can think of the X-rays as having a wavelength lambda. And what we do is we put into the beam our sample of interest. So here is our sample. If the sample had not been in the beam, the X-rays would of course continued along their beam path. And way down the track we have something that we call a detector. Let's label this detector. And we can think of this detector as something similar to the detector inside a digital camera. So it's a two-dimensional frame with lots of pixels. When the sample is in the X-ray beam, some of the X-rays are scattered off at a different angle and hit the detector at a place different from where the beam would have hit if the sample had not been there. And from this experiment, we can look at the intensity of X-rays hitting the detector at different positions. And what we find is that the intensity up here varies depending on what we put in the beam here. Some of the important parameters that we must measure are, first of all, L. That is the distance between the detector and the sample. And also D, the distance between the central point of the scattering pattern and the point where the X-rays end up. We can then use that to learn something about the structure of the sample. So imagine we now take a small region of the sample, very small region, and we magnify that up. If we had a very powerful microscope, what we might see is something like this. The large, well, they would look large, clumps of iron. And let's imagine that on that microscopic scale, the distance between those clumps of iron is characteristically W. We'll call it W. From this, we can write down an equation. Of course, we cannot see this because it's so small, but we can figure out what W is by writing down this equation. W is approximately equal to lambda times L over D. So this equation is the type of equation that we use by measuring these large-scale distances and knowing the wavelength of the X-rays. We can calculate from the pattern D what W is, the structure, the distance between the particles inside the tissue. All scientists, whether they be research scientists, weather forecasters, medical scientists, they all use mathematics as an everyday tool in their scientific work. At school, maths and science are in separate classes, but in the scientific work environment, maths is an essential part of the scientist's toolkit. In the synchrotron activities you are about to undertake, you will be using maths and science together just in the same way as professional scientists do.